Hi everyone, welcome to the third lecture on advanced mechanics. Today we talk about traction and stress. Learning objectives. These are the concepts that we anticipate you understand and be familiar with the relevant equations at the end of this lecture. Okay, first section is introduction. Let's have an example to understand why we need these concepts. I'm going to talk about heart mitral valve. The role of these valves are to prevent the blood from leaving the heart after being sucked in. For example, in this case, you see it has a leakage. Let's take a closer look. The blood is flowing in this direction. Pay attention to this side of mitral valve. It exerts a force to this side like this. We can express that force in terms of force per unit area, aka pressure, and we call that traction, and we show it by T. The traction is defined at each point based on the normal vector, which is the vector normal to the surface at that point. We show it by N. And the traction itself has two components. One tangent component, parallel to the surface at a point, and one normal component, normal to the surface at a point. Okay, let's learn the concept and mathematics behind it. Throughout the lecture, we're going to talk about these concepts. Force and equilibrium relationship, described by a set of equations based on action and reaction, basically Newton's third law. The concept and properties of stress, and it will be introduced as a measure of the force density acting on a body. And finally, principal stress values and directors, external stress values, and spherical and deviatoric stress cases will be discussed. We're going to have help from a few figures that we call Mr. Potato and Pepper family. Stress and its relation with surface and body forces. Stress is a measure of force intensity, and we measure it in Pascal. The force it measures can be body forces like gravity, magnetic attraction, basically any uniformly distributed internal force affecting the whole body. Here, for example, we have the gravity. Or surface forces like any contact or pressure that exerts the force to the body through the surface, like here. Body forces can be expressed as force per unit mass that we show by B or BII, or just simply BI in index notation. Or it can be force per unit volume that we show by P, or again PII or simply PI. And the body density rho relates these two expressions for the internal forces. Simply rho multiplied by the force per unit mass is equal to force per unit volume. Let's expand this equation. We get rho B1 E1 plus B2 E2 plus B3 E3 equal to P1 E1 plus P2 E2 plus P3, E3. Let's see that in an example. Here, can you identify the surface or body forces? So, poking a penguin, that's obviously surface forces. Surface forces that caused breaking of internal organs, like bone breakage here. Here we have body forces. The magnetic field attracts the magnetizable pile of material. Here we have surface forces. A hammer that's pushing a nail into a surface. Here we have body forces. The satellite is under the influence of gravity. Here we have a boy jumping on an inflatable toy. The force exerted by the boy is surface forces. Here we have balloons filled with air. The air exerts internal distributed surface force to the balloon membrane. Let's start by seeing the difference between traction vector and point forces that you know from classical mechanics. Assume here that we have Mr. Potato and a point force and a point moment being exerted on its surface. In classical mechanics point mass system, we simplify the whole system to a point mass at the center of mass of the system, and we assume that all the surface forces and body forces are basically exerted at that point. But in continuum mechanics, we define traction vectors. We can cut a plane, an arbitrary plane, anywhere at any point, and project the resultant force and the resultant moment resulted from those surface or body forces to that point, and define a traction vector. That traction vector is basically the resultant force per unit area passing through that point. We can have infinite number of planes cut through each point of the body, and also we can have infinite number of points inside the body. We use a Cauchy stress principle to define traction or a stress vector at any point inside a body. Let's see how we do it. Let's assume a Cartesian coordinate at point O with unit directors E1, E2, and E3. E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. Now assume Mr. Potato under some arbitrary body and external loads, but no moments. We want to find the traction or a stress vector at an arbitrary point inside the body. So let's cut Mr. Potato at an arbitrary point P with an arbitrary plane with unit director N. Around point P, if we consider a close enough area with area delta S, we can basically find the resultant force and resultant moment at that point. These are resultant forces and moments due to external and body forces that Mr. Potato or any other body is experiencing. Now we can define the traction or stress at point P as the force density on a surface. Pay attention that we define a stress or traction vector in the reference frame, basically the Cartesian frame attached to O. And it is not necessarily tangent or perpendicular to the surface. The same for the resultant force and moments. They are not necessarily perpendicular to tangent or tangent to the surface. If we assume that there is no point moment, we can show that the limit of delta F over delta S as delta S approaches 0 is equal to the traction or the stress at that point. Basically, a stress or traction vector at a point is dF over ds at the point. Since we assume there is no point moment exerted at the body, we can say that limit of delta m over delta s as delta s approaches 0 is 0. Having a look at the traction vector, you see that it is aligned with the direction of the resultant force at the point, and it's not necessarily perpendicular or tangent to the surface. Also, another point to consider is we could cut any other plane through the body at point P. So basically, we have infinite number of cut planes through any arbitrary point inside the body. The traction vector is defined with respect to the normal to the surface at the point. So we can define basically vector pairs of the normal vector and the traction or a stress exerted at those surfaces for any point inside the body. These vector pairs defined the state of the stress at a point P. Knowing the stress or traction and knowing the cross-section, we can find the force that is exerted at that cross-section. Also, knowing the maximum traction in the normal direction to the surface or tangent to the surface, it helps us with designing the structure properly so it doesn't deform or it doesn't break. We can define normal and shear components of traction vector on a surface. The magnitude of normal and shear components of the traction vector T are called sigma n and sigma s. Both are scalars here. So if the traction vector is T, the shear component parallel to the surface and the normal component is normal to the surface. The normal component is simply the traction vector inner product with the surface normal vector. It's simply equal to T1 and 1 plus T2 and 2 plus T3 and 3, and it's a scalar. The shear component, we find it from trigonometric relation. It becomes sigma s square equal to inner product of the traction vector with itself, basically the length or the magnitude of the traction vector minus the normal component to the power of 2. If this is the trigonometric relation, so basically sigma n and sigma s are components of the traction vector t. So basically sigma s becomes the norm of t to the power of 2 minus sigma n to the power of 2. And expanding the equation, we get t1 t1 plus t2 t2 plus t3 t3 minus sigma n square. Principle of action and reaction is something we often use when we work with traction or stress vectors. The principle of action and reaction, or Newton's third law, states that when the body is cut, the force exerted by portion 1 and portion 2 must be equal and opposite to those exerted by portion 2 and portion 1. Have a look here. Assume we have as the potato cut in portion 1, portion 2 through a surface S. The traction exerted by portion 1 to portion 2 should be equal and in opposite direction of the traction being exerted by portion 2 to portion 1. Pay attention to the normal vector of this surface associated with these two portions. On one side, the normal is aligned but in the opposite direction of the normal on the other side. So simply, since the portion 1 and 2 have equal and opposite normal vectors, we can have Tin plus Ti minus n integrated over S becomes 0. Whereas we know T superscript n is the traction vector T associated with surface with normal vector n. Hence, we get the principle of action and reaction, which says that traction on one side of a plane is equal to minus the traction on the other side of the plane, or the traction associated with a plane is equal to minus the traction associated with the same plane but with a reversed normal vector. Here is an example. It asks, when we analyze the stress in body through point P111 and the plane perpendicular to the vector 132 divided by 14, we obtain the traction vector T equal to 8, 10, 7 divided by 14. 1. What is the force F that this surface experiences for an area of 0.0015 square meter? And second, find the normal and shear components of traction vector at P on the plane with unit normal N. For the force, we use the Cauchy stress principle, which says the traction vector is dF over ds. So we can approximate it with the force, the change in force divided by area. So basically the force becomes the area multiplied by the traction vector on that surface. So basically the force is the traction vector multiplied by the area Newton. That's the solution for the first part. For the second part, for the normal component, we do the inner product of T and N, which is basically 8 multiplied by 1 plus 3 multiplied by 10 plus 7 multiplied by 2 divided by 14 square, which is approximately equal to 0.77 Pascal. For the shear component, we use our trigonometric equation. Sigma s square is ti dot ti minus sigma n square. For the sigma n square, it's approximately 0.6. For ti dot ti, we have 8 times 8 plus 10 times 10 plus 7 times 10 divided by 14 times 14. It's approximately 1.09. The trigonometric relation becomes sigma s equal to a square root of 1.09 minus 0.6, which is approximately 0.7 Pascal. Let's review some concepts. First, we talked about body forces per unit mass and volume, and their relation through the material density. Then we talked about Cauchy's stress principle and how we can use that to find a traction or a stress vector. Then we talked about principle of action and reaction and how traction on both sides of a single plane are related together by a negative sign. Finally, we talked about traction, normal, and shear components, and found that the normal component is basically the traction inner product with the normal vector, and we can find the shear component from trigonometric relations. Finally, we have an example question for you to work on during your break. Can you identify normal and shear stress, traction vector, body forces, surface forces, and coordinate system in this figure? Good luck.